그리고 이거 멈춰놨다가 여기
그 엑셀은 엑셀
밑에 있다.
이거 영어로 좀 설치 좀 해주라. 영어로. 출석.
출석부.
응.
출석부.
빈종이 없어? 빈종이. Okay. Let's see. Well, we have an empty seat here. So welcome to seat front. 지난 수업 올렸나?
네, 올렸습니다.
지난 수업? Well, how was the last class? I'm in video. If you have any comment, please let me know. And I'm sure you are invited to a Google Drive where you have to submit your homework in due course. So there will be a homework every week. You should meet the due date, okay? And the Excel file which you submit will be added. So do not submit separate Excel file, okay? There's only one Excel file which you will update every week, okay? Do not submit another new file. Okay, last week we briefly touched about the stress definitions and the material properties. In composite materials, the major difference between conventional material and composite material is the anisotropy, whether I mean material property will depends on the direction. So we need to fully understand the definition of a stress and strain, and most importantly, the relations between stress and strain, which is the compliance and stiffness matrix, okay, which makes the which will describe the material property, especially anisotropy material property. So we need to understand the meaning of being anisotropic and what kind of material property we need to specify. That is the key part. And in terms of defining material properties, we need to also understand the stress transformation and strain transformation and stiffness transformation. That's the key mathematics we need to understand. Mathematics and mechanical or physical behavior as well. Okay, that is the most important part. So anyhow, the stress. As I mentioned, I'm not gonna touch detail about the tensor, but the stress is a second order tensor. Second order tensor means that in terms of tensor notation, we call sigma ij. Okay. Nowadays, there's not much discussion on the tensor notation, but in my opinion, tensor notation is so important, not only in understanding physical meaning, but also in programming. So we need to briefly understand the meaning and symbols for the tensor notation. So sigma ij is the, we can say it's a second order tensor. And this is the simply matrix form, okay? And two dimensions, like 3 by 3. So I and j will be 1 through 3. Or sometimes x, y, z. So I and j, depending on the notation, so it can be called sigma xx and xy and so on. And this is the tensor notations. But sometimes it's more convenient to use a vector form. This is not a vector, but it's a vector form, meaning we just list these 9 components as the 6th component, simply because sigma ij will be sigma ji. It's called symmetric. A lot of physical quantities in terms of metrics are symmetric. Stress are symmetric, and strains are symmetric, and compliance and stiffness metrics are also symmetric. Well, there is the reason for that. It just is not a coincidence. There is a very important physical meaning and reason of why they have to be symmetric. Okay, so these are totally 9 components, but because of a symmetric, we only need to have a 6th component, and we can have many different ways of listing these 6 components, but in most cases we list them in this order: sigma xx and sigma yy and zz and yz and xz and xy. You know why we can easily understand these. If we look at this, x, 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 and y, and y, and y, and z, and z, and also here will be x, 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 and so on. So this will be x, and that will be x, and this will be y and z. So x, y, z. That is the again 3 by 3 matrix, and this can be listed this way. And sometimes we just use one index. In this case, starting from 1 2, 3, 4, 5, 6. So this is the way we describe the three-dimensional stresses. And now this is the a 3D. What if we like to consider only 2D? Well, then certainly this is sigma xx and yy and xy. If we plot, draw these stress distributions, and there will be a sigma x. Okay, this is the x and y and z and x, and okay, this is the sigma xx and sigma xy, right? And well, the other hidden surface there will be a y, sigma yy, and there will be a shear stress like that. So in the opposite direction, there will be a stress like that and stress like that. So there will be a sigma yy and sigma xx. So these are three components, xx, xy, and sigma xy are components in 2D dimensions, xy plane. In other words, z-dependence term, say sigma zz, sigma zy, sigma zx. So this is sigma zy, sigma zx. And also in this surface, there will be a this way and that way. These are terms. Those are related to a z dependency. As you can see here, zz and z and z. So these are z directional dependent terms. So if we consider only 2D, or we can say sigma zz, zx, and zy equal all 0, we call plane stress. Okay, plane stress. These plane stresses can be stress state can be plane stress state when in case this is the, for example, thickness in z direction. If h become relatively very small, I would say very small compared to x-dimensional length or y, then the stress in z direction will be very small. So we can assume that z-dependent term will be 0. So when we list them in 6 components, 2D dependent or 2-dimensional term will be 1, 2, and 6. Okay, so please get yourself used to this notation. Okay, 1 to 6, y 1 to 6. Well, again, in the case of z-dependent, small z-dependent terms. So another point is that these terms, okay, this is the terms relate to x and y. So this is the 1, 2, 3, 4, 5, 6. Now 1 to 6 is the component for 2D. Okay. By the way, I will all the classes are being recorded, and also this lecture note will also saved and upload to our Google Drive, so you can always download. Okay, this lecture note. Okay, well, same story goes for the strain. Okay, strain. strain it should be also 3 by 3, and all the XY component exactly same as the sigma XY, and exactly same as same for the order of this notation, and so on. Only difference you could say plane strain when epsilon ZZ and ZY and ZX, if these three terms are 0, then this case is called plane strain. Okay. Well, why stress and strains are exactly same in terms of a notation? It is because simply because stress and strain are in same second order tensor. See, not because they have a same physical quantity, but as long as some physical quantities are same order of a tensor, all the notation, mathematical transformation would follow the exactly same rules. Okay, I can say sigma ij is also, epsilon ij also second order tensor. But again, I want to emphasize in programming or in Excel program or many cases, it is more convenient to use this a vector form. But physically, you need to understand in stress and strain in terms of a second order tensor. Now, orthotropy. As I mentioned, sigma ij will be epsilon KL and sigma ij KL. Okay, well, why there's ij, why there's a KL? There is a rules for the tensor notations, and ij and KL. Pay attention, this is called free index, meaning KL, they are repeated index. Repeated index means that this one, K equal 1, 2, 3, L equal 1, 2, 3. So as long as this is the conventional notations to represent vector and matrix multiplications. But it is very obvious that KL and KL, as long as they are repeated, we could have this summation notation. So we simply decide not to show these summation symbols. So we just use these repeated symbols, which means that repeated, as long as they're repeated, it means that we multiplied, repeating multiply. Okay, and also this is a second order, and this is a second order tensor, and this is the now fourth order tensor, stiffness. And this is the 6 component, independent component. Strains are independent. So how many terms we can have? Well, we can have 6 times 6, so totally 36 components in stiffness matrix. So each term, as you can see, C11 is a relating sigma XX and sigma YY. But as I said, this IJ represent sigma 1, 2, and 6, and strain. Rather than matrix form, we represent the strain in terms of a vector form. So instead of IJKL 4 index, we can use just a 2 index to represent stiffness. Okay, so as you can see, C11, as you can see, this means CXXXX. And C12, what does it mean? This means CXXYY. So you need to practice a little bit, but anyhow, it's not that difficult. And very importantly, these 3x3 terms are relating sigma c. It is a sigma 3, right? So these 3 guys and these 3 epsilon 3, and there is the 3 and 3. I like to group them into like this, and simply because these 3 terms are related to normal stress component, sigma XX, YY, and ZZ. They are all normal terms. XX, YY, and ZZ, they are normal stresses. And same for the strain. These terms are, I'm sorry, yeah. These are normal stress and normal strain terms. And whereas these 3 terms are shear stress related terms. So as you can see, these first 3 and last 3, first 3 terms are related to normal, and the last 3 are related to shear stresses. Okay? So from here, these 3 terms are normals. So these 3x3 stiffness are relating normal stresses and normal strain. Right? This is the simply matrix multiplications. So these terms are relating normal stresses and normal strain. How about these terms? How about these terms? Well, these happen to be 0 here, but in general, we could have all non-zero terms, and these terms are normal coupled with shear terms, normal and shears. And how about these terms? Shear stresses and shear strains. For example, let's pick the ones stiffness C11 is a CXXXX. What does it mean? Let's say we have a strain. We apply a stress in this direction. There will be a strain in this direction. So if I draw the deformations, so this stress is causing a strain in this direction. There will be some material property relating those terms. That is the term sigma C11. Okay, tension would cause tension strain, or strain cause to cause this much strain. You need to apply this much strain stress. And what is these terms? C12. Well, if you look at the C1, I mean sigma 1 and epsilon 2, which means that when we apply the sigma 1, it deforms not only in this direction, but also, as you can see, do you see the shrink in this direction, right? It's a shrinking. That is a Poisson's ratio. So Poisson's ratio is relating in these deformations and transverse contraction. So sigma 12 or I'm sorry, C12 or C23 or C13 terms relate to Poisson's ratios. Now, how about these terms? Now, this is a very unconventional terms. We may not know before. This is the term relating epsilon 4 and sigma 1, right? So C14 is the relating, say sigma 1 equal epsilon 4. When all other strands are 0, this is sigma 1, for example, sigma 14 will relate to normal stress and shear strain. What is the epsilon 4, by the way? Do you remember epsilon 4? Epsilon 4 is epsilon in terms of XYZ, epsilon YZ, right? Epsilon YZ, get back to you here. This is the 1, 2, 3, 4, epsilon YZ. So epsilon YZ, and this one is the sigma XX. So when we apply the sigma XX, there will be epsilon YZ, coordinate Y and Z. YZ, what is a YZ? Well, this material, if we look, this one, if we look at Y and Z coordinate, okay? So we are looking at this way. This is a Z. This material, originally a scale like that, but this would now deform like that. This is the epsilon YZ, shear strain. So in other words, when you apply the sigma 1 this way, this would deform this way. Of course, isotropic material never happen this way, but the composite materials, it may happen any deformation. It can have any coupling, so all terms can be non-zero. Okay, so each terms would have its own physical meaning, every terms. But again, I like to group them. This guy, okay, these three group first, and then each group. This one is just normal to normal, and these terms are coupling term between normal and normal, and these terms coupling term between normal and shear, and this one, especially this one, is the shear and shear, and these terms are shear coupling terms. And now Cij, again, these are all these terms are also symmetric. So Cij will be Cgi, which means that, for example, Cxy will be Cyx. So this guy and same as that guy, and this guy will be the same as that. No matter how many, no matter, I mean, for any materials, the stiffness matrix should be symmetric. The reason, physical reason, is that there's a thermodynamic requirement. So the rules material property has to obey. That is why in most of I'm sure you do know about the finite element method. And if you have this stiffness matrix relating force and displacement, all the stiffness matrix is the symmetric. One of the main reason comes from this stiffness matrix is also asymmetric. Okay, so this is the stiffness matrix, and it mentioned orthotropic. Orthotropic means now we have a 0, 0, 0, 0, 0, and these terms are how many independent? 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 independent material property. This material called orthotropic. Well, if it's isotropic material, the independent material property will be much less. Okay, so transversely isotropic material. Now, as you can see that, notice that these are same, and these guys are same, and these guys are same, and these terms are relate to 1, 2, 2, and 2, 3. So these terms are relate to this way. So what is a transversely isotropic? Well, just help visualize. Let's say we have fibers, and fiber runs this way, and X, I like to have a coordinate like that, and Z. Okay, let's say we have this kind of material. Then simply these X directional material properties are different from Y and Z, right? In other words, you can imagine that when you have an extension and there will be some deformation, and compared to the other direction, let's say you apply this way and there will be different deformation. So we can easily come to a conclusion that material property in X direction and Y direction, they are different. But Y and Z, this material property in this way or that way will be the same. So that's why Y and Z material property, they are same. And very important, okay? And also these two shear stiffness will be the same in this case. So this is the transversely, this material called transversely isotropic. Okay, transversely isotropic. Why it is called transversely isotropic? Well, if we look at this way, okay, then this Y and Z, those two directions can be called transverse direction, and a material property in any direction, okay, any direction will be isotropic only in this plane. That's why it is called a transversely isotropic. These the material behavior and material property is the one for conventional composite materials. Composite material, imagine this is a long continuous of fibers and layered like that. So in three-dimensional way, fiber reinforced plastic has the material property called transversely isotropic. Now in 3D case, you have this kind of a material stiffness matrix, and let's count how many. Independent, you can say 1, 2, 3, 4, right? Others are dependent. 1, 2, 3, 4, and 5. Okay, so 5 independent material properties in 3D, three-dimensional case. But how about the 2D case? 2D means that in Z direction, this dimension is getting smaller and smaller. So very thin, okay? very thin, and fibers is like that, and fibers are aligned this way. Material property wise, this is the Y and X and Z. Z material property and Y directional material property, they are still same, but stress wise, this thickness is very small, so there is no sigma ZZ. This can be very very small, and also say this stress component, I mean this shear stress component, which is the sigma XZ, right? And also this stress component, which is a sigma YZ, they can be all 0 in the case H is very very small, okay, very small compared to Lx and Ly. I would say this is the Lx, and these lengths are Ly. Okay, so this is a very typical composite layer, which we call a ply. Okay, a ply. So in this case, these are the terms relate to a two-dimensional case. You know, we remember epsilon 1 and 2 and 6. Those are two-dimensional relay strains and stress as well. So these are terms for two-dimensional case. So you can, and also, well, I didn't mention about the compliance, and compliance is the inverse of the stiffness matrix, and also these terms are related to a two-dimensional case. Okay. Now, stiffness and compliance matrix, the point is that how to measure them. How to measure experimentally. For that purpose, we define engineering material properties such as Young's modulus and Poisson's ratio and so on. Now, just relation between compliance and stiffness matrix, sigma and epsilon, and C matrix. Well, there is the A bar here, but I will redefine about this bar. We don't need to pay much attention to here. Simply, S is the epsilon, and S and sigma. So this is the a compliance. Compliance is the inverse of stiffness. So inverse of the stiffness matrix. Now, very important, how to measure this, all the compliance and this guy, you can see that this is the inverse, there is the inverse. And now we can say this is the S11 and S12 and so on, S22 and S6, right? Now, how to measure these guys or these guys? Well, either one will be okay. The other one will be calculated from inverting the matrix. Now, experimentally, this is a very important point, okay? Please pay attention. Now, to measure this material property, what do we do? Well, we usually make a small specimen and relatively thin, and we apply the load. And this is the, we can say sigma X, right? And then do what? We measure. This would deform would deform extension is a sigma x, and contraction, okay, this is the very important point, epsilon y, and also a thickness contraction, epsilon z. So in this case, we are applying stress, sigma xx, and how about this direction? Are we applying any stress? Of course not, but mathematically, we have to think that, yes, we are applying stress, but stress happens to be 0. So experimentally, we are applying all 6 components of stresses, but happen to be just one component is a non-zero, others are all 0. Why this observation is so important? Because S matrix, pay attention to S matrix, we are applying the stress component, meaning that we are applying the stresses here, and we are measuring some strains. So experimentally, what we measure is the compliance, not the stiffness. There is no way to directly measure this stiffness. Why? Well, to measure the stiffness, I mean the C matrix, what we need to do, we need to apply, for example, 1, 0, 0, 0, 0, 0, right? And then whatever you get, stress will be sigma 1, 2, 3, and so on, and sigma 6. And these guys will be simply C11 because we are applying one component, any terms, right? But imagine how we apply this type of a strain. Only one strain, and this way, the strain have to be 0. Is it possible to make them make strains 0? Extremely difficult, right? We have to hold them. We have to hold them, not to contract. Experimentally, it's not possible. Well, this is a very simple observation, but very critically understanding material property. So the way we apply the stresses, sigma xx and sigma z, and even sigma xy equals 0, and sigma zy and zx, all 6 components, we are applying stresses, okay? And so whatever we measure are the strain, and strains are measured, which is the direct terms of compliance. Okay, so that's why we are measuring the S11. So, for example, the term we are measuring, epsilon x, when we apply sigma x, will be S11. Don't pay attention. Sometimes I use x and sometimes use 1. Sorry for that, but it's not so, it's very trivial at this point. So anyhow, what we measure in strain is the, since we do apply these stresses, what we measure is the compliance. But conventionally, the way we define the stiffness is the Young's modulus is a sigma equal E epsilon. That is the conventional definition of Young's modulus, right? So that's why we can say that this is the strain and stress relation, and this is the what? S11. Okay, so we are measuring epsilon 1 from experiment, and simply we are measuring compliance. Okay, all the compliance directly from material property, engineering constant. and put it here. How to get the stiffness? Well, numerically, we inverting the matrix. Okay, actually, this is what we covered the last week. Simply 6x6 matrix and all the material properties. And see, is E1, E2, and G12 and G23. Where is well, these terms, well, missing here. But anyhow, it's S12 is related to a Poisson's effect. Okay, this is just a sum of terms. Okay, well, this is the intentionally copy from theoretical manual of the ANSYS. ANSYS, or even Abacus, or Nastran, any tools, you name it, exactly follow this. And sometimes X and Y and Z, or sometimes they use 1 to 6. That's the only difference. Other than that, it follows the notation we just described. So this is very important to understand. Actually, this is the S matrix. And sometimes instead of C, they use a D matrix, okay, just a symbol D. So as you can see, you find from material database is the E Young's modular X. And in matrix, it goes like that. This is the compliance and EX. And now we have so many different Poisson's ratio. I mean, in isotropic material, you can say just 1 over E, mu over E, and all Poisson's ratio will be the same, right? But imagine, go back to here. Let's say we apply here. And this will certainly extend like that. But it also certainly, it shrink. Imagine how much the shrink, I mean the ratio between this strain and this contracted strain, that is the definition of the Poisson's ratio. Now we are applying this stresses, this will simply extend it, right? So this will be a amount extension, and this will be a contractions. So ratio between extension and contraction, that is the definition of a Poisson's ratio, and simply this direction and that direction will be different. I can give you some rough idea of the value. When we apply this way, this fiber is very strong, okay, very strong, and the shrink is in matrix direction will be about 30%. Same as the metal. But in this direction, in Y direction, when we apply this load, this will extend, but these shrinkages will be very small, because the fiber, they like to resist to deform, contract. Okay, so these strains are so small. How small? Well, for example, this EX, for example, 100, and this EY, so usually I would say 10, then this is the 30% is 0.3, then this contraction will be 0.03. That is about the order, and And simply, I will use this notation, this one. Okay, I will just use this one. Imagine, pay attention to these terms and these terms, okay? And we do understand EX, X directional stiffness, Y directional stiffness. Now, very important term is this Poisson's ratio. New XY is called major Poisson's ratio. So when you enter this value in ANSYS and Abacus, don't get confused. You have to look at their own theoretical manuals, because Abacus, ANSYS, they may call this one mu YX, sometimes mu XY. So you have to pay attention or look into manuals. Anyhow, here, mu XY goes to here, mu YX goes to here, and simply these have to be symmetric. So these terms, mu YX is simply mu XY divided by EX and EY. So that's why I said this is a 100, and this is a 10, and this, if this is a 0.3, then this will be 0.03. So there, this is the not just a relation. They have to follow this symmetricity, and these have to be values. So when you enter the value, you only enter this. You don't need to enter all of them. You just E and Y, and usually this is the same value, and you enter this, and as you can see, this is all the same, and so this is the same, and this is the terms, and this is the terms. Well, it could be all independent, depending on the material property you like to solve. Okay. And these are all now stress and strain terms. You can see that on the left-hand side is the stress. On the right-hand side, all the strain, right? All the strain, which means that if we invert these terms, okay, we invert these terms, and then this C matrix will be the S inverse, and C11 can be in terms of engineering constant. So this will be, okay, this will be a terms for the C11. Well, I don't think you need to remember this. Only need to understand this engineering constant. Okay, engineering constant, these terms, and compliance and symmetrics, you just numerically calculate it. Okay, so basically this is what we covered last week, and it comes two-dimensional transversely isotropic, which I already explained. So this is the condition. We have to have these three terms are 0, which means that these 2 by 2, well, this is the a normal terms, and these are shear terms, and these are normal and shear coupling term. And of course, these 3 guys are normal coupling term, and these 3 the shear coupling term. Now, in 2D case, two-dimensional case, we only consider these terms and these terms. Okay, so we will mainly work on these two-dimensional transversely isotropic. So you can always come to reference and refer to all the 3D definition, but again, most of the theory which we will cover in this course called classical laminate theory. We consider only very thin ply and stack them together. So sigma ZZ, ZY, ZX can be neglected. But in advanced course, those 3 terms can be huge. I will cover at the end of the course, but for now, we just consider only plain stresses. Okay, so sigma 1 to 6 now can be called sigma x instead of sigma xx. Okay, it can call sigma x, and this we just call sigma y and sigma s. S stands for shear. Okay, shear S. And now strain same epsilon x and epsilon y and epsilon s. So instead of all 6 by 6, we just use these 3 terms, and these 3 by 3. Now you need to understand how these terms came from. So this one is from this guy and this guy. I'm sorry, I forgot this one. This is also important, 0, 0. Okay, so which makes 3 by 3. Now, how about the stress in terms of strain? We have to invert this S matrix. Don't, please, not, you would have this C matrix 6 by 6, and if you bring those terms, these are wrong. Okay, don't get value from here. These values need to come from this a 3 by 3, and you simply invert. The main reason is that, again, these 3 terms, or these 3 terms, are from assumption that sigma y, ZZ and ZX and ZY are 0. That's why we can neglect, see here, we can neglect we can rewrite here. We can neglect the terms, which means epsilon, S matrix, and sigma. This is a 6, 1 by 6. These are 6 by 6. So from this 6 component, we are assuming plane stress and only 3 terms. So this assumption need to apply to here when we multiply. So we take only 3 by 3 term from here. Okay, not from the not from this relation. Okay, why? Because there's no way to apply strain condition in measuring material properties. Okay, we always apply the stresses to get the material property. So all the Young's modulus are coming from these relations, and also these stress assumptions are coming from can be from these relations. Okay, so this is the one we we call stiffness of UD composite. What is a UD? UD is the fibers align one direction, unit directions, and fibers will be like that. So this one conventional we call X, and this one Y, and this is a Z. Or sometimes, in most cases, I prefer to use fiber runs in horizontal directions. So this will be the X and Y and Z. So Z coordinate is no longer needed. Okay, so we often neglect this one. So in terms of stress, okay, in terms of stress, sigma XX, YY, right? And sigma XY. Okay, those are three terms, and those terms comes from here. And strain in plane direction, X direction strain, Y direction strain, and shear strain comes to here, and material properties goes to here. Okay. Okay. Like to go back to Excel, which we played last week after 10-minute break. Okay. Okay. Say these are compliance in terms of engineering constants. Of course, a two-dimensional form. So strain, 3 strain, and 3 stress. And now here, 1 over EX and Poisson's ratio, mu Y, and Poisson's ratio, mu X. In ANSYS, as you saw that it's sometimes called YX or sometimes XY, but we don't need to use those two index. We just use Y and X. Okay. So these are of course, X directional Young's modulus, Y directional Young's modulus, and Poisson's ratio, and these are symmetric, so these have to be same. And this is a Y stiffness and shear modulus. So how many independent stiffness? We can count them. 1, 2, and 3, and 4. Okay, 4 stiffness or material property relate to a stiffness can be measured for very thin ply. Now, how to we're gonna cover? We're gonna study a little bit about how to measure those terms. Now, this is the transversely isotropic, well, two-dimensional version. Now, this term can become isotropic. So in case of isotropic, we simply 1 over E, Poisson's ratio E, and 1 over E, and 0, 0, 1 over G. These are terms, compliance for, oops. This is the terms for the isotropic material, right? We already know that. So as you can see that, well, X directional and Y directional, we do have a different Young's modulus. That's one thing. And Poisson's ratio wise, well, these are these term and these terms even though they are dependent, but they have a different meaning. So we need to understand. So another one, very important, is the shear modulus. And this shear modulus G has relation with Young's modulus and Poisson's ratio. So independent, number of independent is only Young's modulus and Poisson's ratio. Well, of course, there is a clear reason why there is a relation between shear modulus and Young's modulus Poisson's ratio. Simply this way material property and this way material shear modulus. Oops. There's many different ways of explaining these relations. One simple way is that let's consider pure shear stress or strain relations. And this is the exactly same as tension and compressions. Say this is a sigma in terms of magnitude. And so this is the minus sigma, this is a plus sigma. So why these shear stresses are identical to this normal tension, normal compression in 45 degree. This is the 45 degree. Well, if you look at the, I hope you do remember the Mohr circle. Mohr circle, this shear stress is here. And if you rotate 90 degree or 2 theta, which means 45 degree, this is exactly tension and compression. So how much you apply the shear stress in 45 degree, one way will be compression, the other one will be tension. So this is the tension and compression. So this one is exactly same as the identical stress state. Well, this Mohr circle, where does it come from? Well, it comes from the stress transformation. Stress transformation. What is a stress transformation? As I mentioned, as I emphasized, the meaning of a stress compliance and transformations are critical in expanding the concept of isotropic to anisotropic. Well, composite is certainly belong to anisotropic, so we need to understand stress transformation. Okay, I like to, this is so critical, I like to briefly explain what is a stress transformation. In order to understand this, the meaning of stress transformation, we need to understand what is the A scalar, what is the A vector, and what is the stress. Well, in terms of order of a tensor, this is a zeroth order tensor. And this is a first order tensor. This is a second order tensor. So what is a tensor? Well, there's a little bit long story, but it's all related to a transformation. For example, temperature or density of a material. We have a material. okay, in three-dimensional space, X and Y and Z, and there is the a positions. Okay, this is X vector. There is a positions. Now here we do have some material property. Okay, material property. Now the material property, let's call temperature. Okay, temperature. Now to indicate or to explain or to show that temperature, we can use this coordinate system, or sometimes we can use a different coordinate system, which rotate from a reference coordinate. So the temperature here, okay, temperature here is independent of this coordinate system. So if you look at the temperature or measure the temperature in XYZ coordinate, or I would say X prime, Y prime, Z prime coordinate, this temperature, I would say, okay, I will use okay, this temperature will be the same as the temperature in different coordinates. So it's independent of a coordinate system. In other words, let's say we have a body, we have a temperature here, and somebody is standing here and look at this temperature, and my reference coordinate system will be this. Also, temperature will be 20 Celsius. Now there is another guy which is standing in this direction and coordinate like that, and to indicate that temperature, what will be the temperature? Same, 20. So this temperature is called scalar. Well, same for the density of material. We have a density there, will be an independent coordinate system, right? So these are characteristics of a scalar variable, scalar quantities. Now, let's consider other one. For example, I will delete this one, not to cause any confusion. Okay, we define or we apply certain load. This much load applied to that point, and this force. Now, in terms of XY, we have a X and Y and Z component. But this F is just stand there. But in terms of a different coordinate, this coordinate, the coordinate, this will be simply different. Okay. In other words, say here there is a certain force is applied here. Now, I like to explain or say the component of this force. So I use this one. So this will be, X is this much, Y is this much, and Z is this much. But other person with a different coordinate, for example, like that, would explain this force, same force, with a different component. For example, I only have an X component, which happens to be parallel to this force. So indicate the same force, depending on the coordinate system, component will change, right? The key point here is we explain same physical quantity, which happens to be a force, or sometimes a velocity, sometimes acceleration. Same quantity, but different component depending on coordinate system. So there is a relations. What is the relation? Well, Fx, Fy, Fz and Fx, Fy, Fz, they are not the same. I'm going to delete this. Oops. Is the fx just for to distinguish them from others? I'll use the prime, okay? Y prime and fz prime. And now, depending on the rotated angles, there will be some terms which we call often call beta ij. So this is the terms relating those terms to physical quantity. For example, if we look at the just 2-dimension, 3-dimension is a little bit complicated, but if we look at this just 2-dimensional terms, this is a 0, and I'm sure you saw these relations. Oops. Fx and Fy and Fz. Okay, Fy. So these the relations, and simply we use x and y and okay, I will use different color. I will use this x prime and y prime, and use x and y, and I will use this guy as the black. Okay, this is a physical quantity, and f is just here. Okay, again, f is just stay there. F does not change, but depending on the coordinate system, the component, for example, component will be this much, and component in this much. Simply each component will change, right? So this is the relation, and this is the called vector transformation. So don't get confused. We don't rotate the vector, but we simply change the coordinate. The component of the which describe the physical quantity will vary or called transform from the previous component. Okay, that's the meaning of the transformation. Now you can extend the concept to here stress, but unfortunately, it's not easy to show stresses at one point using some kinds of one arrow like that. So to indicate stresses over here, the only way we explain the stresses is just use a small volume, and then here we have the stresses, okay, like that. But now, depending on the coordinate, two coordinate system, and we rotate this volume like that. Oops. Use this one as the x component, y component, z component. Then we have a little different components. Okay. This is the component, and So these the components. These three component, I mean the 3 by 3 component, the 3 by component, they are different, but stress here is the same. So this stress can be in terms of x, y, z coordinate, or can be in terms of x prime, y prime, z prime. The component will simply change. That's the called stress transformation. I hope you do remember the relations. One of the, for example, sigma x prime equal cosine square, and sigma xx plus sine square, sigma yy, sigma, no, twice of cosine theta and sine theta and sigma xy. And there is also a sigma terms for the sigma y prime, I mean, something like that. Okay, this one, fx prime, cosine theta, this and that. This is the terms relations. Okay, so there is a little bit of a mathematics involved. So this is the very important explanation about the stress transformation. And one step further, we do have a stiffness matrix or compliance matrix, which is the fourth order tensor. And now we have a little more complicated transformation. You remember, pay attention here. This is a cosine theta and sine theta, just one order of cosine and sine. But stress transformation, you have a cosine twice, sine twice, and cosine sine. Always second order, I mean twice of times of either cosine and sine. So fourth order tensor, you will have 4 times cosine, cosine, sine, depending on the terms. Okay, so these are very important concept of the stress transformations. And now these terms, okay, this is the terms for the isotropic, and these rules, okay, these stresses and this strain, and this is the a compliance would follow their own stress strain and stiffness transformation matrix. Okay, so for the isotropic material, this would become like that, and sorry, this would become like that, and inverse of this, okay, inverse S, this is S, and inverse it will be like that. Determinant, by the way, this term is a little bit complicated. Well, we don't need to remember, but in terms of just a symbol, this will be like that. And also in isotropic, these terms, isotropic, will be E1 of mu square, because this will be the one. So I'm sure you often notice terms E1 over mu square for the isotropic material, and we need to understand why these terms. Certainly this term is different from just Young's modulus. So in two-dimensional case, there will be a Poisson's ratio effect compared to just one-dimensional. So anyhow, we will go back to this observation more deeply later, but this is the compliance matrix for the transverse isotropic, but this stress and strain and all the compliance matrix would follow this old physical transformation. These terms are, this definition will be, transformation rules will be used next chapter, but I explain a little more in advance. Okay, so how do we measure these guys? Epsilon x, Young's moduli x, y, and Poisson's ratio. Now this is the test we use. Again, please pay attention again. This is the epsilon x, okay, epsilon s, and this the 1 over ex, y, and x. Well, it's a little bit confusing. It's either y or x, but you don't have to remember. It just always refer to a reference. Okay, this is the stress. As I mentioned, okay, well, this look a little bit awkward, but in imagine real specimen, you make a little bit long and slender specimen. Imagine you have a steel made of steel or aluminum specimen, and you apply the tension. You sometimes have a tap, or sometimes you have a dokbon style. This is the test you apply. How much or how you apply the load? Well, you apply the sigma x. That's what you apply. In other words, if you look at here, you only apply sigma x. That means you apply zero stress. This is the one very important, which means that you allow freely contract. Even thickness, there will be a free contraction. So the point is that we are applying the stresses. That's why this is the matrix. We are applying these stresses, and these are terms we are measuring. The other way is not possible. Okay, if stresses comes here, strains comes here. If we apply the stress, well, it's a little bit complicated. Or can we apply the strain? Not possible, right? You have to hold them together sideways, constraint, and you apply. That's the only way, but experimentally, it is not quite possible. It is a very obvious, but it is important to observe. So we are applying this sigma x, okay? Sigma x, we are applying only sigma x. So sigma x and 0, 0. That's the terms we are applying. And then now we are measure the epsilon x. So this is the what we are measuring. Okay. Well, as you know, this is very simple equation, but you do need to know how and where these terms comes from. And also, what you measure is the epsilon y equal minus mu y ex and sigma y, sigma x. But this is a symmetry, you can use the same term. Okay, this is the what you measure, and this is the what you measure. With specimens like that, you have an extension and you have a contraction. So contract terms will be like that, and extension will be like that. So here, sigma x is in terms of a strain, that will be okay, ex. Sigma x in terms of a strain, what is that? EX from here, epsilon X. So simply what we measure is this one. So definition of notation is a little bit. You know, definition, as I mentioned, can be okay. Here we use EX and UX, which means that here we use the X, right? And here the same term, but here mu Y E Y. So epsilon X Y will be this one and that one the same, and we do have these terms. Well, you don't need to worry too much about the definition of Mux. You always get to this precise the definition depending on the text and depending on the software. Okay, so we can see that simply. Okay, I need to use this one as the Y. Okay. No, this one should be X, 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 and X. Oops. X. So if fiber runs this way, when we apply this, and I'm trying to help you understand the value, and this contracted is the Parsons ratio, which will be about the 30%, very similar to a metal. Okay, in fiber direction and contract in transverse, that is a 30%. Okay, so this is the material property we measure. Now, the other one is the transverse directions. And now here we apply the sigma y, okay, sigma y, and which means that we apply sigma x equal 0. Of course, the sigma shear is also 0. So in previous definition, I will rewrite here epsilon x, epsilon y, and epsilon s. 1 over x minus mu x ex, 0, 0, 1 over y, and 1 over es. And now we are applying 0, sigma y, and 0. So what we measure here is simply these three guys times this guy. So epsilon, of course, you are using the strain gauges attached in this direction and strain gauge in these directions, rosette sometimes, or extensometer you attach. So what you measure is this one, and this is the one you measure from strain and stiff stress. So this slope in y directional stress and y directional strain is simply Young's modulus. Okay. Now another one. Of course, in here you can measure the Parsons ratio, and same as here, you can measure the strain x and y direction. But one thing you need to remember that mu x ex should be same as the mu y ey. Okay, this guy, y and ey. So these are a relation. Okay, one last term we need to measure is the shear stiffness. Shear stiffness. Well, we apply the sigma S shear stress. Again, similar to previous, we are applying sigma Y, sigma X equal 0. Okay, and that's why we, but this guy 0, 0, but happen to be there is a 0, 0, 1 over E X and mu X and E X and 1 over E Y, and only terms are from this guy. See, this is a 0, 0, and that. So this will be 0, 0. We only will measure the shear strain. So when we apply this, the shear strain will be like that. Shear strain in terms of geometry is nothing but angle change, right? Angle change is the shear strain. Length change is the normal strain. So we measure strain and angle. Well, it's not easy to measure the angle change. So what you need to do is that you use the 45-degree rosette strain gauges, and strain gauges is only we measure the extension length. So use the strain in 45-degree, or these days we often use a DIC, digital image correlation, which means that we spray, make a lot of dots, and then we using the camera, we trace each point and it changes the strain. Well, these are two camera, stereo camera, and sometimes we can use just a single camera if the plane is just plane. But sometimes curved structures, we spray a dot, for example, like that. The only reason we spray them is that we make a random note, random dot, and then the camera will trace each point, so that camera and data and each point the movement, and we simply measure strains. Not much. For example, here, this is a specimen, and we spray them. There's not much skill needed to spray them. You spray, and then using the camera, we measure all the displacement. Just before and after is okay, or you just trace deformation, and you get the strain. Okay, very useful way of measuring the strain. Well, not quite shown here, but sometimes automotive, you have deformations, and sometimes I don't know what is this, but you like to measure the skin when you deform. You spray them and you change the skin, and it show us. I mean, it measure the strain distributions. But anyhow, nowadays DIC, digital image correlation, become very popular. But still, strain measurement is still widely used. Okay, so this is the shear stiffness. Shear stiffness, relating shear stress and shear strain. Shear strain, again, let's say we have a 90 degree and we have a certain angle change here, alpha and beta, and this epsilon s is simply alpha and beta plus. And that is the engineering strain, not the tensor strain. Okay, so we do have all 4 stiffness: 1 epsilon x, Poisson's ratio, epsilon y, and epsilon s. Okay, that is the old story about the material, 4 material property, which you already survey from internet, and this is the kind of database you could have. So epsilon x and Poisson's epsilon y and Poisson's ratio and shear stiffness. The magnitude is usually gigapascal. So for the steel, where's the steel? Steel is a 200 or 210, 10 to the minus 9, 10 to the 9 gigapascal, but you can simply say 206. And 206 and 0.3, and shear modulus for the isotropic, you can calculate it, right? But others are all independent material property. What are those terms? These are terms relate to strength, which we will cover next about in 2 months, okay? So don't pay attention to these terms. So let's get back to Excel. Well, not much complicated. Oops, what is this? Okay. Okay, so this comes from where? Well, this comes from this EX and EY and G. So these are material property. We'll go to here and then multiply here and then and so on, right? So these are material property, and we like to have them in separate database, which you open to update, or you like to have as many as you like. So in Excel, for example, this is not complicated procedure, but very useful. Say this is EX. EX and EY and Poisson's ratio UX and ES. Okay, this is the term. And now like to access, but I will use this table. Okay, I'm sure you have your own database, but I just use this table. Okay, and by the way, this material name, as you can see here, there is always fiber/matrix. Fiber/matrix. That's the conventional way of represent our name composites. So AS4 is very typical carbon fibers, AS4, and PK is a peak, PEEK, poly FF cation, is very good thermoplastic material. So anyhow, N56 is very conventional epoxy, and N55 another epoxy, and all so on. Scotchy is happen to be a brand name, glass epoxy, but it's been widely used. But it no longer is not quite used. Kevlar epoxy, AS4 peak, IM6 is another fibers, another carbon fiber, and epoxy, and T3 means T300. You know, Toyota, I mean, not the Toyota, Thoery. Thoery have started with the T300, 700, 800, T1000, and F93 is the another epoxy, and still, and this is the another epoxy. So let's say just use a T300 epoxy and T700 epoxy, just T300. Well, these happen to very high stiffness, 181 and 10.3, and Poisson's ratio is a 0.28. Oops. And EX is what? 7. Well, we cannot remember all the values, but will be good to remember order of I mean the ranges. Okay, so T700 here no value for T700, but I would guess like a 150 or 10. I mean, precise value you can always refer from the reference. Okay, and this will be like about 10. Now, I like to, as I mentioned, extend this Excel file, and you will program and you will develop your own tools so that you can calculate stiffness or strength of all the laminate, any angles you liked. So that's why I like to start from the material database and then refer to this value and define the UD material property, which we cover this today. So let's say we range them this much, okay, enough ranges, and this one like to well, it's always good to have these ranges, and top rows and first column is just, and then this range is the dB, and I will call material dB. Okay, this is the material dB. So as you can see that index material dB, comma 1, comma 1. Okay, simply when we need to refer to this value, we use the index. Well, in Fortran and C, there will be different way, right? You declare the dimensions and you call them using the index. Well, whatever language you like, use, you just simply follow the this one. Okay, let me change. I like to change this. This one was defined as a range, but I like to cover this name as well. Okay, this first one, because sometimes we want to use the a name and to how to change this this one. Well, you may think that if I just select, you type sorry, it's material DB, same name. Oops, does not change. Okay, so the way you change is that go to formula, and this is the name manager, and you list all the dimension you declare. So go to a material DB, and then as you can see here, this is the worksheet name, and this is a range, and you simply change this one as what? B. Okay, so as you can see here, 1,1 now refer to a name. And I will just call this one as the material. Right. But don't worry, it will automatically change this a name of the worksheet as the material whenever you change it. Okay, and this one I like to enter as the main worksheet. Now, main worksheet. Now we're gonna study all the theory and we're gonna program. Okay, now. Well, I always like to use a different color. As you like. And always, this is the, not just Excel, this is a software. In software, coding is important, but more important is maintenance, maintaining how you maintain, how to upgrade, and so a help file is so important. Okay, so say this is the version number and date, what you changed. So today is the 21, 22. So anyhow, this is the not so important. Okay, so in main, now I like to say specify. I like to choose T300 or T700, and then later we will stack them with a certain angle and certain as how many and so on. So this will be first ply, second ply, third ply. Now we just consider 8 ply, stack them, okay? 8 ply. So this will represent first ply, second ply, third, and so on. And then we will make a laminate and we will apply the load. That's what we're gonna do. So this is the first ply. And now in the first ply, what you want to choose the material. So this is a material number. What does it mean, material number? Material number means that, say you select 1, means that you want to select first material. Say this is 1. And up to 10, you can easily extend it. When you want to extend it, you simply drag and insert. Then this ranges is automatically increased. So you don't need to redefine. So anyhow, this is the name, and go back here and material. Say I would like to use just a symbol, a simple symbol, and MAT. So MAT, and now this one is important. This row will have a name called MAT. Okay, MAT. How to do that? We just select and this, and now this will have an automatic name, MAT. Oops. This is the MAT. So I like to use the old same first material database, and just for the purpose of showing material name. Now you can see that here, index material DB it's not easy to type here. Okay, whenever you have a enter name, this predefined symbol will automatically pop up. So you can select them. And comma, remember the matrix of a material DB. This is the name will be the first and MAT. So MAT will simply refer to this number in here, this case. And if this is a 2, and this simply copy and paste, and this will be no, it's not right. MAT, comma 1. Why? MAT is the this MAT, and go to here. MAT is the this one. So MAT should be first a index, and the second index should be a name. So copy and paste. Then this, if you choose the 2, this will be simply T700, right? Well, this is not so important procedure, but I like to build up, keep using this Excel programming, so it's an important step. So this material, this is the data you enter. And this is the material name. And now you like to refer to EX. What is the EX? Simply, the material is this one, right? And instead of 1, we enter 2. Now we call EX times gigapascal. So the way we program will be, we only need to do is just the first column. And this one, the rest of column, we just copy and paste. So here, and y, and these terms will be simply 3, and this will be 4. Oops. We don't need to multiply this value. And this is the EX, right? Now, well, you can copy and paste. And depending on this material you chose, and this we can easily refer to name and material properties. Now, for next programming, what we like to do is that define this guy as the EX. So EX and EY and so on. So this is the how we select, how we name them. So as you can see, we select them, it automatically has a name EX and EY and so on. Now back to theory. If we like to use this guy, like to program this one, okay, this is the stiffness. I forgot to mention, for two-dimensional stiffness, instead of C, we use a Q, okay? C and Q, they are same, but just for the purpose of two-dimension, we just use a Q. So Q XX, Q XY, Q YY, and Q SS is now, you can say, what is this? 1 over, just follow the symbol, EX, oops, EX divided by 1 minus mu X times EY divided by EX. Okay, so this is the value for QXX. And pay attention to this value is slightly larger than EX because these terms are in 2 dimensions and these terms are 1 dimension value. And for make simplicity, let's say this is a determinant. So we use this as a I mean, we don't need to, but programming-wise, it's always better to make coding simple. So this one, and then this Y, you just use a Y. Oh, sorry. Is Vx, right? And then here and Y, and here simply ES, not X. Okay, so if you select any value here, we only defined 1 or 2. As you can see there, material properties are automatically called, and stiffness in this case for this 1, 2, 3, 4 term. Sorry, 1, 2, 3, 4 terms are called and calculated. Okay, this is the this is the terms relate to UD. Well, we can color them later, but so far, theory-wise, we cover up to here. That's the UD stiffness. And you may wonder, oh, this is a 3 by 3. Why we use this a column vector? There is a reason for that. Is simply what we're gonna program is just a first column, and then just copy and paste. And so as you can see that we all you need to do is just a program, first column, and then rest of them will be very easily obtained. Okay. Now, let's go to a little bit about this next chapter. Next chapter is the off-axis stiffness. Let's continue to class and then end in 20 minutes. Is okay? Okay. So chapter 3 is the off-axis. Okay. What is the off-axis? We didn't define this name. We just call UD. What is it? By the way, PowerPoint, you can define a section. And here, as you can see here, on-axis stiffness is about UD stiffness. Okay, UD stiffness is the topic we covered. Okay, that's called on-axis. This a terminology. On-axis sounds not familiar, but this is the on-axis. And off-axis. Now, what is off-axis? Okay, off-axis is the axis with rotate with a certain angle with respect to on-axis. In other words, let's say the purpose of this chapter is that now fiber is a certain angle. Axis is like this. Now, remember, this is we call X. X is always along fiber, and this is the Y, transverse direction. Now, I will call this is X1 and X2. Sometimes just 2, sometimes just 1. So 1 and 2 is the called reference direction or off-axis direction. Okay, and now what we like to do is that we have fibers aligned with a little tilted directions, and now we want to apply certain stresses. And what will happen? And you can estimate, while certainly there will be certain strain in this direction, and there will be certain shrinkage in this direction, but at the same time, this would have a shear strain. Shear strain means that this guy will have change in angle. Angle will change. So here we apply this stress will be called sigma 1 rather than sigma x. Okay, sigma 1 we have now epsilon 1 extension and contraction and shear strain, all 3 terms. Now the point of this chapter is the off-axis stiffness. So epsilon 1 to 6, and X S11, S12, and S16, which was a 0 in on axis UD, right? There's no shear strain. And sigma 1 and sigma 2 and sigma 6. And this guy, sigma 22, and I'm sorry, S22, S26, S66. Now, this is called off-axis compliance, and this off-axis stiffness will be just a inverse of this S matrix. Okay, so this is the off-axis stiffness. Okay, so as I briefly explain about the strain transform, stress transform, and material property transformation, now we need that theory. We need that observation. See, in the isotropic material, we have a reference, XY, or we do have a different reference, and they have a angle, rotate by theta, two different coordinate systems. Now, to indicate material property somewhere here, for example, vector, the vector that this theory was briefly explained, but mechanical property of isotropic material do not change. Okay, do not change, which means that here is isotropic and material property, compliance and stiffness, they don't change. Regardless of this coordinate system, the material property will be the same. That's the story comes here. And here, as I mentioned, we have a S1 and S2, X2, and S and Y. We do have a angle. This is a pi angle in general, pi angle theta. This is the value you design as a designer. You chose this angle. You select the material. You chose this theta. Very important variable. So on axis is XY, fiber and transverse. Off axis, sometimes called X1, X2, and sometimes X prime and Y prime, depending on this notation we need to define. Okay. Well, this one I already explained, so we can go through quickly. So this 3 by 3 and strain. I forgot to mention about this too, because this is all tensor strain, and now this one is the engineering strain, and this is the tensor strain, but in vector form. It's only difference is 2. Why do we bother with the tensor or engineering strain? It's simply because we are used to define shear modulus like that, sigma, and this, in this case, this one, we often call gamma, and this guy we often call tau. So when we define the shear stiffness, we used to use tau and gamma. This gamma or epsilon is not this guy, but twice of this. So this is just a convention. We used to define the material property using this shear strain. So nothing special, but we need to be careful. So in two-dimensional, this one, this, and that. So in off-axis coordinate, we apply sigma 1, 2, and 6. This is a stress we apply. And now strain we observe epsilon 1, epsilon 2, epsilon 6. and this strain would have a relation to this sigma, and this is called compliance in off-axis coordinate. So this is the compliance. So we multiply this S and sigma, and this, in terms of stiffness, we invert this compliance, and this is the stiffness matrix Q. Now we understand why there's a bar. Bar stands for off-axis. Okay, just bar stands for off-axis. Okay, so this derivation of off-axis stiffness. This is the vector transform, which we briefly touched, covered. There's a vector in two different coordinates, and this is the sine and cosine. And strain and stress, the Mohr circle and transformations, simply this is a given, is epsilon 1, epsilon 2, and this is epsilon 6. And these are strain. Oh, how much the strain in on axis? Okay, so this is the, again, strain transformation. Please don't get confused. Strain, in other words, there's a material have a deform. So strain at that point, which exists, okay? It's very difficult to explain, but there is exist. But now to explain that strain using this coordinate, that coordinate, only the component will vary. Strains are there, okay? That's the definition of a strain transformation. So say we are given this strain. How to transform? Well, simply strain transformation rules, and this is the M, where M is the cosine theta and sine theta, and this is the matrix. Okay. So cosine, sine, remember this is the same, and so this will be twice of cosine, sine, and epsilon, x prime and y prime. Okay, so there is several equations relating on-axis strain and off-axis strain. Now, same story goes to stress. Exactly same. So there will be a stress given, okay, sigma x, y, and s, and this is the sigma what? 1, 2, and 6. So if these are given, what, it can go this way or that way, simply inverse of matrix, and this is the on-axis stresses. Now, pay attention to this matrix and these matrix. Well, they look a little different, aren't they? They are a little different. Why? Only reason is that because of these two. Okay, same tensor rules, transformation rules will apply, but only because of these two, there is a slight difference. Imagine that if we have in the shear term, I'm sorry, this is not the 3, this has to be 6, okay? In the shear term, if we have a 2 and 2, okay? This is for the shear, strain case. So these 2 divide, and these 2, we multiply 2 and 2 and 2. This will be the transformation for this okay, so divide this, so this term will disappear because of this two. So as you can see here, if we have a twice of the shear strain, shear terms, this transformation will be exactly same as that one. Okay, well, it's not easy to remember. You don't need to remember. You always refer to equations. Okay, all you need to do is just understanding where this relation comes from. Okay, now this is the final terms. What we like to do is to obtain this Q bar, off-axis stiffness. You know, we obtain Q in on-axis. Like to show again in Excel. What we have done is to obtain this on-axis stiffness in terms of material properties. Now, what we like to do is that we enter here. We like to enter angle. Okay, angle is the one we like to specify. So, we like to this one as the angle. Now, say this is a 10 degree, then this ply will have a rotate by 10 degree. So this is using this angle, we like to transform this Q into off-axis coordinate. That's the what we're gonna do. Okay. So back to here. Again, concept is that Q, definition of Q is relating sigma and strain in off-axis coordinate, Q bar. But Q bar is not a new material property. This Q bar has to come from this on-axis material property. How? That's the one, final relation we like to drive in these chapters. To do so, we need to, all we need to do is use the stress transformation and strain transformation. Just follow this path. Okay, this goes to here, which means that this relation. But this strain guy comes from this, or the other way. So from here to there is the, from here to there, this is a transformation which was defined in here. So rather than just going from here to there, we like to go here, here, here. So all these three steps will be same as this one step, right? This is the starting point, and like to relate to a stress. So that's the definition. To obtain this definition or relation, we just go through this, and so as you can see, in other words, sigma and sigma, there is a transformation, and this sigma has a relation with the strain in on-axis coordinate, Q, and this strain is related to off-axis transformation. So finally, we got sigma bar in terms of Q epsilon bar. So this is the three-step, conceptual three-step is nothing but off-axis stiffness. Okay, 3 times matrix multiplication is the same concept as this material strain transformation, over on-axis stiffness, and stress transformation. That it can be considered as a direct relation between off-axis strain and off-axis stress. Okay, so to make this okay, so final form will be like that. You can certainly go through and try, but don't bother. You just use these terms. So simply say Q11 is now M4. What does it mean? M? Cosine theta, right? N is a sine theta. Okay? So let's just use a M is not a good symbol. I would like to use cos. Okay? Cos means cosine. But cos is a cosine angle, but angle we like to use a degree, but we like to change the radian, right? So just the pi divide by 100 degree, okay? Or you can okay, this is the cosine and also sine. So this one will be a sine. So we name these rows, and now Q11 is simply equal what? Cos 4 power over 4, right? See M4, M instead of M, I use the cos. Because just one character, name for one character is not good. So I use the cos. And multiply what? Q XX, right? But oops, we didn't name this guy, so we just have a name. And this one. So this will be the first term, and second term will be a QY, a sine first power and QYY. So use the sine and QYY, and then say 2 and QXY and 4 times. Okay, yes, be patient. Okay, and here and what? Q XS, right? So this is the one for strain transformation, the stiffness transformation. Well, just for the purpose of a double check, we entered the angle 0. What will happen to a Q11?
Equal to Q.
Yes, Q will be the same as the QXX, right? Well, what if we enter 90 degree? What will happen? Q11 will be QYY, right? Okay, so that's the meaning of this stiffness transformations, and now we can cover all kinds of stiffness variations. And it's not too bad. We just copy 1, 2, 3, 4, 5, 6, and paste. And here will be 2, 2. Well, you can type it. Okay, so this will be your homework. And now I'd like to show you this one. We just change it to all kinds of this way. See, let's say 10 degree, 20 degree. Okay, first of all, I like to use the same material, all number 1, and I like to specify 10 degree, rotate by 10 degree, 20, 30, and 40, 50, 60, and 70. Oh, I like to add more. How to do that? You just simply like to 2 column and insert and simply copy and copy and paste. Okay, so again, name is automatically extended. Whenever you insert the expand the ranges, name will automatically expand it. So as you can see here, we can increase as many as ply we like to extend, even 100 ply. You can easily extend it, right? You can just here, and then you can just insert, then whole ranges will be, okay, so that comes, okay. Now, I'd like to show you some value, so 60. This is the 70, and this is 80, and this is 90. Now, say this guy, Q11, copy and paste, and as you can see here, this is the 0 degree, Q11 will be what? QXX, and 90 degree, this guy will be simply QYY, case 90 degree. So let's select this guy, and oops, this guy, and this one. I use the control button. You can select the 2 separate rows and goes to insert, and this is the how you plot them, and this is the how change the Q11 over the angles. As you can see again, 0, 180, 10 to the 9. Oops. Is simply QXX, and here very low, as you can see how it change. Well, just 2 minutes more. I like to enter these terms. This. So not much change. So we just change this one as sine, right? This one has the what? Cosine. That's it, right? And then we just copy and select and paste. Now we like to plot them all and imagine what kind of plot you're gonna have. This is exactly what we expect. Q22 is the simply QYY for 0 degree, and then increase to a QXX for the 90 degree, right? So again, like that, and like that, and simply this is a theta, and this is a theta equals 0, and theta equals 90 degree. So 0 means that like that, and 90 means that vertical. So you can imagine how this stiffness will change. I didn't plot others. For example, Q66, Q66 will be something like that. So all terms will vary according to angle. Well, okay, I leave something for you, okay? So please type, enter the equations here and plot them, and please, you already have all the dB, and you complete and name this worksheet as your own tools. I will each class, as I define, as I mentioned, will develop, and will be very useful tools for you to analyze all the composite layups. It's called classical laminate theory. Okay? Okay, any questions? Okay, well, this is the homework 2, number 1 of homework 2. Okay, I'd like to again assign another homework 2, second problem of homework 2. I will send through Kakao. But be sure to submit all the homework to a Google Drive. You have your own Google Drive folder, right? So please be sure to submit on time, because whenever you upload, the time is automatically reported to me. So don't forget the submission time is also important. Okay, so thank you, and see you next week.
네네, 안녕하세요. 수업 중이라서 전화 못 받았어요. 예, 제가 지금 사인 받아서 30분 내로